I won't make you write it this time because you've written it like 20 times, but this whole time we've been thinking about the 4 different kinds of conic sections that come when you vary the values of the eccentricity, right? So we know these to death by now, so I'm not even going to say anything else about them. But what I asked was, okay, what's actually going on, and in particular, why is the order of the shapes circle, ellipse, parabola, hyperbola? What's actually visually happening? Because so far, we haven't really connected this idea. We've said it's a ratio, yeah? But it doesn't have much to do with the actual, like these are something to do with cones. So the question is, what, right? So therefore, how are we going to picture this, right? Now I'm actually going to ask you to draw something for me, which is a cone. Okay, draw yourself a cone. At the very beginning, we defined for ourselves what conics were. There's a conic section, short for conic section, which is short for cross-section of a cone, right? And you can kind of see some of these are easier than others. You'll have to draw really well here. I'm going to try and draw a cross-section, right, by imagining a plane that cuts through the cone. Planes are 2D shapes, cones are 3D, so I'm going to get a cross-section. So here's how I'm going to draw it. Okay. So I want you to try and imagine that thing slicing right through the middle, okay? Now, this is the first one I'm going to draw, and then I'm going to bring out some props. But because it's quite easy, it's literally right across. If I wanted to say it, would be parallel to the plane, that is. It's parallel to the base of the cone. Okay. So what kind of shape are we going to get from here? We're going to get a circle, aren't we? Okay, because I could cut the cone, if I cut it parallel in that way, I'll get a whole bunch of circles. I'll get really small ones up here, and then they'll keep on going until you get to the bottom, which itself is also a circle. No problems. Okay. Now that's where we started. So last time we looked at this thing, wake up. We looked at this thing, right? And we had a look at what happened when we started with the eccentricity being really little, and that's why we had that quite circular looking shape, right? I can make this a bit brighter, I think. Hold on. There we go. Okay, and then as we increased the eccentricity, what happened? Well, I can do this, I think. Yeah, there we go. Our shape became more and more fat. It became more of an ellipse. It always was. Oops, I went too far. Okay. So we had this kind of thing happening, right? Now, therefore, what's changing with regard to the cone? How do I get these kinds of shapes out of the cone? Well, I can't cut it in the same way, can I? How would I have to cut it? How would it change? I'm going to have to, any way I cut it across, I'll still get a circle, right? But the way I can get an elliptical kind of shape is by cutting it at a different angle. Okay, so draw yourself another cone. All right? Now this is where, unfortunately, paper's going to let us down a little bit, because we can try to draw this, but it would be very hard to do well. Okay, so I'm going to try and draw something like this. Okay, so I'm seeing it going across at an angle, right? Now if you picture in your mind having a cone there and taking a knife and slicing it across, I don't know if you guys are, it's a traditionally Asian sort of thing where if you have a cucumber, right, instead of cutting it across like that and getting circles, right? Yeah, Asians are cheap, so we're like, no, we want to make it look like the cucumbers are bigger than they really are. So you cut it in diagonals. Now you can sort of even see off the diagonals that what you're going to get is going to be longer. See, it's longer, right? But I haven't changed the diameter, the height of the cucumber, if you like. So what's going to come out is something that's longer, but it's sort of, well, it's elliptical, isn't it? Okay, and you can sort of picture cutting it. So this is how the shape would look. It'd be off at an angle. Okay. Now, I told you the paper would let you down, so I brought something that wouldn't. So here you go. Here's a cone. Okay, and there's my cucumber slice. Can you see it? Right? It's elliptical because I went off at an angle. Okay. Now, sense tells you that as we change the angle, like right now, you've got sort of, what's the angle of this slant height? It's pretty high. I don't know, maybe 70 degrees or 60 degrees or something like that, okay? And this angle looks like kind of 45 or so. Looks like that's where it would be. But as I increase that angle and make it steeper, okay, the shape you're going to get is different, right? We started with a circle, then we got this elliptical kind of thing, and at some point, well, what happens? And what's the point? Draw yourself another cone. At some point, these ends don't connect anymore, right? And that particular point is where you've gone so far that instead of being our plane parallel to the base, this one, our plane just being off at an angle, this plane is parallel to the slant height. Can you see that? Not just the one line, but the whole plane itself. Okay? So you're going to get this kind of shape. It doesn't reconnect at the end, right? It should look something like, which one is it? I'm going to pick the right one. I think it's this one. There we go. Does that look about right? Does the slant height look about parallel to the plane? Can you see it? And there you go. There's the shape. Okay. And that's the parabola that we're familiar with, right? Here we are. Okay. So we have one last case to consider, the one that we've just most recently been looking at, right? So what's the logical conclusion, the fourth step? Come on, people who went to the UMAT evening. Let's complete the pattern. If I was parallel to the base, off at an angle more so I'm parallel to the slant height, what's my last one going to be? Now here's the thing, right? Remember, look at these. These values correspond to something here. Remember I said for these, to get a circle, your plane has to be flat, exactly flat. Not a little bit off, has to be flat, which corresponds to the fact that there's only one value for eccentricity that will give you a circle. Okay? Now here, you've got a bit of range, right? You can have more circular ellipses, or you can have fatter ellipses, depending on how you slice the cucumber, right? So that corresponds to the fact that you have a range of values for the eccentricity. And I can change that angle if I like, right? Here, it looks as though you could get a whole bunch of different parabolas. But what we know about the pattern so far is that you can't. There's only a single kind of plane, right? A single angle for this plane has to be exactly parallel. That'll really give you a parabola, okay? So what does this suggest? How many angles can I put that plane at to get a hyperbola? The answer is I should be able to do a whole ton, right? Like more than just this single value and this single value, okay? An easy classic way to think about it is just to make it vertical. I'll make it vertical. Here's my plane now. Okay, what kind of shape are you going to get? Well, you start from this end, you're going to go here, be like, hold on, I feel ripped off. That's not hyperbola. That's half a hyperbola. Right, so therefore you need two of them. Okay, make sure I get the orientation right. Now unfortunately these don't connect together, so I'm just going to have to hold them really carefully. But there's a double cone, okay? Can you see it? There you go. So if I spin it around, there's the hyperbola shape that we're familiar with. Now what happens, how would I get different kinds of hyperbola with different eccentricity? Where would the plane go? You can change it in a couple of different ways. You can move it around, like for instance, if I moved, you're looking at it there, right? So you're kind of off to the side, but I can move, whoa. I can move this plane horizontally, can't I? Right? If I move it in, can you see these 2 points here? By the way, what's this distance? It has a name. What's that distance? We're used to seeing it this way, aren't we? That's the transverse axis, right? The transverse axis is going to get smaller, right? It'll still be a hyperbola, okay? So we can change that by changing this horizontal position, okay? Or alternatively, we could still be off at a different angle so long as we're not exactly parallel to the slant height, okay? Yeah, question?
What happens if it's like that perpendicular, but then it like goes through the point?
Right through there.
The point, yeah.
Yeah, through there? Yeah, okay, good question. Excellent question. What would happen? We're picturing, excuse me, two cones sitting on top of each other, a double cone, if you like. So if my plane did go right through the middle, what would it look like? what would it look like? If it's going right through the middle, I guess these things should touch, shouldn't they? But what kind of shape would I get? Think about it carefully. Think about it really carefully. Look at the cone. I'll hold up where you get cones, rather. Okay. Remember, if I cut it right through the middle, okay? What's it going to look like? You're slicing it in half, aren't you? Now, we're going to draw this in a second, but I think I can do something better. I said that the board and your paper would let you down, right? Because you're trying to do 2D. This is better. This is an improvement, okay? But it's also letting us down because this is one ellipse and one ellipse only. But we're trying to think about things as they change, right? Okay, so let me see if I can do this. You might like to edge forward now. This is the one I want. Okay. Let me try and make it as big as I can. Okay. How many of you can see that thing? Can you see it? Can you make it out? Let me try. I can make it a little bigger than that. There we go. Okay. I need a little further up. Full screen. There we go. Okay, great. All right. Can you see it? So there's the double cone. Okay. Now, have a look at what's there right now. You can see there's a little red shape. What is that? That's a circle, because what kind of plane do I have? Which one of these is it? It's parallel to the base, isn't it? So this is our first case. Okay. But what kinds of things can I do here? Ooh, this is a first. All right, I'm going to, I've scrolled off. There we go. I'm going to vary, for instance, where I am vertically. Okay, so I'm going to think about these cases now. What would you expect to happen? What would you expect to happen? The size of the circle, the magnitude, its radius should change, right? So let's give it a go. Okay, let's go down, shall we? Okay, there we go. Good. And as we get to the base, if I can get to the base, there you go. There's the biggest circle I can make. This one's a different one. And I can go all the way up, and if I can keep my grip, and I'll get a different circle. Great, no problems. Okay, we'll come back down to the bottom cone. All right, now, what if I try and move across here, right? I need to change the angle at which the plane is cutting the cone, aren't I? So let's try and move this guy over a little bit. Okay, can you see it happening? Can you guys actually see the screen? Yeah, okay. So now you can see, there we go. There's our ellipse, okay? Now hold on a second. I said there's a whole range of values here, and there's only a single one where you actually get to a parabola. So here's my question. What if I move to, say, there? Okay, now you can't read it, but probably. But my rotation angle is 33 degrees at the moment. So that's the angle off from the base, right? Now I'm pretty sure they've drawn this cone so that the slant height is at 45 degrees. So it's nice and even, okay? So I've got a plane at 33, and I've got a slant height of 45, right? Now, what kind of shape does that look like? It does look like a parabola, doesn't it? But you're being fooled, okay? I'll tell you why you're being fooled. If I have, this won't do it. Let me look around. Who's got something? Can I have your headphones, please? Okay. Now, let's try this. I should have brought something longer with me, but as I said, I was having a bad day. I'm going to make a shape here, okay? And I want you to tell me what you think it looks like, okay? Let's see. Okay, there's an easy shape. What's that? What kind of line is it? It's a straight line. Okay, so it's a linear function. Okay. All right. Now I'm going to put it down to about. Let's do. Clearly, this thing has been in too many knots, but you get the idea. Imagine it a little bit smoother. Okay. What kind of shape does that look like? It does look like a parabola, doesn't it? But it's not. It's not. You can take a shape. You can take a picture of it. And you can try and match a parabola to it, and you'll get close. But you'll never get there, because this shape is not a parabola. This shape has a completely different name. It's called, not that this is part of the course or anything, but I don't even know how to pronounce that. I think it's a catenary. It's the shape of an object that's hanging under its own weight. It looks like a parabola, really does, but it's not, and the maths will prove it. Okay. Now this thing also looks like a parabola, but why? Why does it look like a parabola? I think the only reason it looks like a parabola, and not like the ellipses we got before, is because go brighter, is because it stops, it ends. It's not full. It doesn't come back around on itself, right? But if you look really closely, imagine if I drew this kind of shape. Right? Like so. Okay. Now suppose you knew, actually let's do it horizontally because that'll be a bit easier for our math. Suppose I could tell you, without a shadow of a doubt, that kind of thing, that'll do, okay? By differentiating or inspection or whatever, that the tangent here, I missed, the tangent here and the tangent here are parallel, okay? Now, on some inspection it looks like a parabola, doesn't it? Because again, like the shape you just looked at, it doesn't complete, it doesn't come back around, okay? But you can tell me it's not a parabola. Why not? What's the reason? Can we articulate it? Because a parabola can't what? Parabola can't. Parabolas have this kind of equation, right? So when you differentiate them, you're going to get a function like that. Okay. Now, no matter how far you go with this parabola, okay, put in the largest values of x that you like. You will get very, very high, but you'll never get to what kind of gradient would correspond to these kinds of things. For these, it'd be 0, right? So I guess I'm thinking the other way around, x's and y's swap. For this, it'd be, there would be no gradient, because vertical, isn't it? The parabola can never get there. So I know that in this shape, even though it doesn't come back around, it's actually not a parabola, it's really part of an ellipse. It's just I don't have enough of the cone to show me the ellipse. Okay, does that make sense? So you can tell by the curvature. The curvature tells you. All right, now I'm almost done. That was the ellipse here. Okay, what do I need? What do I need in order to get a real parabola? Well, I said the slant height was 45, didn't I? Okay, so let's get up to there. 45. Okay. Now you're like, really? I can hardly see a difference. Let's move this up a little bit. No, wrong. There we go. Okay. So to us, to our eyes, we can't tell the difference, right? But this is one of the great things about maths, right? You don't need to trust your eyes. You can trust the equations, and you'll see what's going on, right? In fact, when we do these, when we try these out, we know the equations are completely different, right? Something might look parabolic, right? But we know from the equation it's got a y squared in it, so it can't be. Okay. Right, there's my parabola. Last one. Let's have a go. Right, what angle should I give you? Let's go. Whoop, there we go. Too far. Okay, so you can see it cutting through both ways, right? You can also see you don't necessarily have symmetry between these. What would that correspond to? Like this part and this part are not equal. What would that mean for a hyperbola that we could draw? It does match the conditions for a hyperbola. Sure, looks like a hyperbola, right? So far, all the shapes we've been doing, we've been imagining quite nice and neat, right? So things like this. Oh no, I'm saving that one for Ruben's question. Things like this, you know, because they're easy cases for us, okay? So everything's nice and symmetrical. But there's tons of places where there isn't that kind of symmetry, right? I can just move this across. Maybe I'll just move the axis. There you go. It's still a hyperbola. It's just as hyperbolic as before. I haven't changed the shape. Okay, bless you. But it's not equal, are they? The branches are separate. Okay, very last question. Let's come back to Ray's question. What's going to happen if we go right through the middle? Right through the middle. Now, let's see if I can do it here. Well, let's see if we can try together. I want it to be. Whoop, there we go. Can I get it close? Now, hold on a second. Let me go back a little bit. I want. Oh no, I'll take the same angle. Let's just go further. There we go. Okay, so now I'm cutting across. I'm going vertically. Okay, going vertically, and you can see the shape there. But I want you to tell me. See if you can describe for me if you can see it well enough. Not only are the branches of the hyperbola getting closer to each other, but they're changing in a particular way, right? So let's see if I can move this slowly enough for you to tell me. Have a look. They're coming in, there we go. And I think you can probably see the change about there. Can you see? Do you need me to go back? What's the difference if I were to draw these? Right? If I were to put these on the same graph. Actually, no, forget that. I don't need to do that. I've already got it here. There we go. Okay, I'm going to increase the eccentricity like so. There we go. All right. Now, have a look at that guy, right? And as it increases, they do get closer together, but have a look at the lines. We said this before, do you remember? They don't look so curvy anymore. In fact, the further I go, the less curvy they get. As they approach each other, as the transverse axis gets smaller, then necessarily the lines, they get a lot straighter. In fact, if I covered that, it almost doesn't look curved at all. It looks like two straight lines, doesn't it? They're approaching the asymptotes, right? Now, when I actually get together, it breaks, okay? But you guys can picture it, can't you? Can I hold it up one more time? If I were to cut these exactly in half, we've been saying that they're going to get straighter and straighter and straighter and straighter. Eventually, they become straight, don't they? Whoop, that's terrible. Wow, okay. You just have to forgive me. There you go. Now it's messing up and you can't tell. Because that's what the cross-section of two cones looks like if you go right down the middle. Because you chop it in half. Look, see, there's the cone, and there's the other one. Okay? Now, evidently we can't get there. It breaks down in a similar way that this breaks down. This is really just an idea. It's really the limit as E approaches 0. But you get the concept. Okay.